Okay, example number 2, the integral of ln x dx, where here it's recommended that we take the u to be ln x, and this is dv. So let u equals ln x, therefore du is 1 over x dx, and dv is dx, where v is then x. dv is simply integrated to get to v, so just integrate dv, it should give me x. Now the rule is that the integral of u dv equals u times v minus the integral of v du, and therefore this integral will give me u times v, which is x ln x, minus the integral of v is x, du is 1 over x dx. Now this x can remove the other x, and then I can have this as x ln x minus the integral of dx is simply x. So this is my result, and I can add c here, and I'm done. Okay, now going forward, I will take this example, integral of t squared e to the t dt, where I have two different families of functions, the exponential function and the polynomial function. Of course the dt is common for both. So here, if I take t squared as u, meanwhile the rest as dv, then I would say here let u equals t squared implies du is 2t dt, meanwhile dv is e to the t dt, and hence v is e to the t. E to the t is invariant under integration, so when you integrate it, it gives me itself. Now uv is t squared e to the t, then minus the integral of v du, 2t e to the t dt. And here notice that I had something that is a bit similar, or of the same species of the initial integral, except that the t squared now went down to t. I downgraded the power of t to become, instead of 2, it became 1. This is the benefit of this technique, but still I'm not done. We need to do this one more time to get the t to the 1 down to t to the 0, which is a constant. So I will take this integral, I'll call it integral number 2. If I'm calling this integral number 1, and this is integral number 2, so here I can say that number 2 is twice the integral t e to the t dt. And again I need to redo the integration by parts. Here I'm calling this u, I'm calling the rest dv, and one more time let u equals t now, therefore du is dt, and e to the t dt, I'm calling it dv, and therefore I have v equals e to the t. Put this back in the integral. This gives me uv, which is t e to the t, and then minus the integral of v du, which is e to the t dt. Now don't forget that there is a 2 here, so I will keep it multiplied by this, and therefore I can then distribute the 2 and evaluate this integral. This becomes 2t e to the t minus twice the integral e to the t dt is e to the t, and this is integral number 2. Putting this back in here, I return back to the main integral, which is I equal, let's call this I here. So I is t squared e to the t minus, now whatever in this circle here should be replaced by the result I determined here. 2t e to the t minus 2 e to the t, and once I'm done, I have no more integrals to do. Then I can add plus c, the constant of the integration. Now this can be cleaned up, as I can distribute the negative here. So t squared e to the t minus 2t e to the t plus minus minus here is plus 2e to the t and plus c. Notice that I have e to the t in each term here, so I can take it as a common factor. So e to the t times t squared minus 2t plus 2, and then plus c. This is my answer for the original integral, which is